Hello students, welcome back. In the previous video, we went through the definition of the linear operators, eigenvectors, and eigenvalues. We went through some examples as well. Now let's talk about how to find eigenvalues. It turns out we can find out all the eigenvalues using this matrix equation, which we call characteristic equation. Y is a big deal, but we'll probably end up proving it later or maybe next week. I have it here in section 3, so probably this week. Example first, finding eigenvalues. Find all eigenvalues of the given matrix. Oh, the same matrix we saw before. Okay, let's go ahead and do that. Determinant of A minus Ti. So this is A, and then minus Ti is here. So this can be written as multiplied by T, and then I can remove this. Oops. So we end up with this determinant, and appropriate subtraction, I get minus T on the diagonal entries and no change in anything else. Okay, let's go with this determinant computation, and here we go. Crisscross method, alright. Principal diagonal, 1 minus T, another 1 minus T, 2 minus T. Oh no, excuse me, I didn't use crisscross method, sorry about that. Looks like I used the expansion with respect to row. Okay, 1 minus T, and then the determinant of the deleted matrix, minus 2, and the determinant of the deleted matrix, and finally 3, and then the determinant of the deleted matrix. That equals to 0. And simplify. Well, okay, how do you simplify? The key is do not expand everything all at once and then try to refactor. Let's simplify step by step. Okay, keep 1 minus T here and simplify a little bit further after, 0 kills off everything, and further. Okay, and that do not completely expand over 1 minus T, 2 minus T, and then 1 minus T times 3, okay, we have there, and then here's the rest, and then keep it here for the time being, and this part, keep simplifying, okay, keep simplifying. You ended up with 6T minus 12, which is 6 times T minus 2. You see, if you completed breaking this part off, then refactoring would have been a bit harder. You may have to break everything off later on, depending upon a problem, but most of the time, break it off only when it is necessary. So what we have here, T minus 2, okay, factor that T minus 2 out, and what's left is this quadratic, and T minus 2, okay, I'll get one characteristic value here, T equals to 2, and from the other, I'm going to get these two, 1 plus square root of 6 and 1 minus square root of 6. How do you find out characteristic vectors out of these two characteristic values? Well, we went through those already here. For lambda equals to 2, here we go. Remember? For lambda equals to 1 plus square root of 6, here we go. Please do not expect a problem like this in exams. In homeworks, yes, but in exams, you're going to end up with rational numbers most of the time. Don't worry too much about bogging down in computation. How about the next problem here? Okay, that looks a little bit more challenging. We have a 4x4 matrix here, but still doesn't look too bad. We have 0, 0, 1, 0 here, so whenever we calculate the eigenvector here, excuse me, the characteristic equation here, the determinant computation will become not too bad. Okay, ready? Determinant of a minus ti, so I'm subtracting t from diagonal entries. Let's go to the previous problem and let's see, 1, 1, 1, and there used to be t here. A minus ti, and ti we get t, and those are subtracted over there. Likewise, we do the same thing to this principal diagonal. Minus t, minus t, minus t, minus t. Everything else stays the same. And let's do the determinant computation. And obviously, I'm going to select the third column here. Okay, 0, 0, 0. They're all gone, and I have 1 minus t and the determinant of the deleted matrix. Okay, how about this deleted matrix? Well, I can use a crisscross method here. No, I didn't do that. Again, I didn't use crisscross method here. Again, I expanded with respect to the first row here. Negative 4 minus t, and then the determinant of the deleted matrix. Negative 2, and then the determinant of the deleted matrix. Negative 2 here, and then the determinant of the deleted matrix here. I'm wondering why I'm doing this. Crisscross method is a bit easier. And after some simplification, do not break up everything all at the same time. Keep as much as possible in case you'll have to factor it back. We have 1 minus t and then some further simplification. Looks like we are getting something like these. And am I getting t minus 4 or 4 minus t? No, I'm not getting that. This is minus 4 minus t, so it's not a common factor. Looks like I need more work, but still I have at least 1. From this factor, I'm getting t equals to 1. Okay, that's a baby step, alright. And then I'm going to select this brace is equal to 0, and that's going to be the second step. Okay, t equals 1 I got, and from this equation here, let's break these up. And again, the idea is break off only those are necessary. So break off the second, third, like these. And then, do we have something further here? Square minus square looks like t minus 4 plus 2, t minus 4 minus 2. Consequently, it looks like I'm getting t minus 2 as a common factor. From here, I'm getting t minus 2. Combining these, I'm getting negative 24t minus 2, so t minus 2 is common. Factor it out, I get this quadratic. Now t minus 2, alright, another baby step. We got t equals to 1 here, and t equals to 2 there, and then this quadratic. And get that quadratic done. I'm getting t equals to 0, and another t equals to 2. So here we go, we have all the eigenvalues. Lambda, lambda equals to 0, which I got from the last step, and lambda equals to 1, which I got from the first step, and lambda equals to 2, there's 1, and then there's another lambda equals to 2 from over there. So these are all characteristic values, all eigenvalues. There are 4 eigenvalues, but 2 of them are duplicate. Now, what if you want to find out eigenvectors from these 4 eigenvalues? Do we have a problem like that here somewhere? Let's do it. there's good chance we won't be able to complete it in this module, in this video. But what the heck, let's do it. 0 times this. So x, y, z, w. Oops. Okay, all right. Let's solve that for the first eigenvector. So first eigenvalue is lambda equals to 0. So 0 equals to that. Okay, all right, let's solve it. So we have negative 4x minus 2y plus 0z minus 2w equals to 0. Right hand side is also 0. And then next, 6y plus 4z plus 6x plus 4y plus 0z plus 2w is equal to 0, okay. And then negative 6x minus 2y plus 1z minus 3w is equal to 0. And finally, the first row, 6x plus 2y plus 0z plus 4w is equal to 0. Okay, so we don't need this 0 part. We don't need this 0 part. And can we simplify? Let's go ahead and do some of these. Looks like I can add first row and the second row together. So if I add second row to the first row, what do I get? 6 minus 4, that's 2. And as a matter of fact, before that, some simplification. We have all even here, so let's simplify. Divide by 2. 1, 1. Divide by 2. 3, 2, 1. And that 2. Divide by 2. Okay, we have a little bit better form. Excuse me. Okay, and then we're going to add first and second. So add them up, and then I get 3 minus 2, so x, and then 2 minus 1, so plus y, and then w minus w, that'll cancel each other out. So I get x plus y is equal to 0. There goes 1. Y equals negative x. That comes from the first line. Now, is there anything that I can get? Anything else that I can get? I can subtract the second line from the third line. 3x minus 3x, so that's going to be gone. No, simply third line, second line minus. So just subtract, so that's 0, gone. Subtract 2 minus 1, so that becomes 1. And then that becomes minus w. 1 minus 2. So that's what we get. All right. Y equals to w. We got that too. So y equals to negative x, y equals to w. So what am I getting? X equals to negative y, and w equals to y. Okay, we have, okay, what do you do to the second line, third line? Let's see, I'm kind of running out of ideas, so why don't I just add these two up? Add these two up. So 2y, 2y, that'll cancel each other out. And w, that's going to cancel as negative 2. And negative 3 minus 6, so negative 3x. That's what I'm going to get from this third line. Let's see, what do we get here? Oh well, let's put these into second line and third line respectively. Let's see. 3x plus 2y plus w equal to 0 minus 3x plus c minus 2w equals to 0. And let's see, x is equal to negative 2y. Okay, negative y. And then w equals to y. Okay, and then how about this one? X equals to negative y. And then w is equal to y. And this one will not give you much. Negative 3y plus 3y is equal to 0. So we get 0 equal to 0. That's trivial. It doesn't give you any additional information, which is natural. From here, I'm gonna get z. Let's see. 3y plus c minus 2y is equal to 0. So z plus y equal to 0. Am I getting z equals to negative y? Let's check. That's positive. Unless I made a mistake somewhere. Looks like it's going okay. So x is negative y is y, and z is negative y, and w is y. That's what we get. And then we can, oops, putting in y equals 1, we get minus 1, 1, minus 1, 1. Looks like we got an eigenvector for eigenvalue 0. Do you have enough time to check? Let me pause this video and then write down some mathematical program. Let's check. Okay, I paused the recording and I typed in mathematical code. I mean, these are not really linear algebra, just mathematical programming, so I didn't want to take too much time. And yes, it does turn out correctly. So the computation we just did is correct. Everything fits. The difference is zero matrix. So everything is correct. So let's go back here. So 8 times a vector is 0 times that vector. So we set up system of linear equation. And we do some elimination. We did a lot of eliminations, typically using the second row the most often, and then reduced into several substitutions.